welcome everybody. Thank you for inviting me again. So as we mentioned before, it's exactly 35 years, definitely by the month. I don't know by the day that I gave my first talk in this esteemed seminar. And so I'm very happy that, well, I would be even more happier to come to New York in person, but in this way it's easy to make this possible. So I'm going to talk about triangulation flip graphs of planar point sets. So yeah, of planar point sets. This is work with Uli Wagner from Austria, which happened last year when I was there on sabbatical in so-called pre-corona times, fortunately. And so what I will do in the talk, most of the time I will explain you the result, and give you some context. And in the end, I will even say a few words about the proof. So let me see. Yep. Good. So let's start right away with triangulations. So even if you know what a triangulation is, I think it's important for the talk to do this carefully. Actually, there are three types of triangulations I would like to talk about for the context. So there are full triangulations. So anyway, so as a starting point, we always consider finite point sets in the plane, and we assume general position. I will say something about this general position at the very end. So no 3 points on the line. And what is a full triangulation? A full triangulation is a maximal plane straight line graph on P. So you start connecting points, and you keep doing this without creating crossings until you cannot continue anymore. And what you get is what is a triangulation, and we call a full triangulation. So a partial triangulation is pretty much the same thing, with the only exception that you can skip some of the points. You cannot skip the vertices of the convex hull, so which I call extreme points. So in our example, there are 3 extreme points which I cannot skip, but others I can potentially skip. So here you see a partial triangulation which skips 2 of the points of the original point set. And there are regular triangulations, also known as weighted Delaunay triangulations, probably in the computational geometry community. So these you get by taking your points, which are points with 2 coordinates because we are in the plane, giving them your favorite third coordinate. In this way, you lift the points to 3 dimensions. And then you take the convex hull, and what you see from below is a partial triangulation, actually. And everything you can get in this way, you call a regular triangulation. Observe that I was writing here a generic lifting. What I mean by this is that I do not like 4 points in the lifting to be coplanar. And if you have these conditions, then you get a partial triangulation. So I will have a picture on the next slide. So it's pretty obvious from the way we described it that every full triangulation is a partial triangulation. So this is just a partial triangulation which skips none of the points. And every regular triangulation is a partial triangulation. It's not so obvious that there are actually partial triangulations which you cannot get by lifting. So there are partial non-regular triangulations. Actually, the triangulations I showed you here in the middle is not a regular triangulation. So we will probably not go into much detail why this is not a regular triangulation, but it's important that not everything, not all partial triangulations are regular. And when it comes to convex position, so if the points are actually vertices of a convex polygon, then all the three notions coincide. As I said, the extreme points you cannot skip in a partial triangulation. So every partial triangulation actually has to be a full triangulation in that situation. And you can also quite easily convince yourself that every triangulation of a convex polygon is actually a regular triangulation. So you get it by lifting and projecting down the lower convex hull. And of course, at least these triangulations have been investigated since, at least since Euler in the middle of the 18th century. So these are the three characters. And now let's see what we learn about them. So here is an illustration of the lifting. So you have the points in the plane. So like here, the points in the plane, and you lift them, and then you take the convex hull, and then you project back the edges of the convex hull, and then you get the triangulation. So this point here in the middle was lifted too high, if you like, and in this way it does not appear on the lower convex hull, and that's why it is skipped. So that's how you get the partial in the triangulation. And I stole this figure from the book on triangulations by Jesus de Loera, Jörg Rambau, and Paco Santos, which is kind of the book with all the basic and definitely much beyond the basic information in this topic. So what we want to look at and consider is the set of all triangulations of a point set. I mean, there are many reasons to do that. One, for example, is in applications, you have triangulations which you like and which you don't like. In some applications, you don't like large angles of triangles. In some applications, probably you want to have short edges. And so you want to find the best character. And so you want to see what is the universe of all possibilities. So here is a point set, 6-point set, 6 points. So a regular pentagon, it looks like, with a point in the center. And here are all the triangulations you can get in this way. On the top, you have probably the most natural triangulation in a certain sense. And here in the bottom row, there are all the triangulations which skip the middle point. And actually the middle point is the only one you can skip in a partial triangulation. So of course, if you want to work with this, you would like to have structure on this set of all triangulations, just similar to, for example, if you look at 0, 1 sequences of a given length n, we know that the n cube provides structure, which is the same structure you get on all subsets of an n element set. And in order to do something similar like the cube for the 0, 1 sequences, remember in these two 0, 1 sequences in this graph are connected. If they differ just by one element, we need something like a notion of a minimal change. And that is what we call a flip. So we're approaching slowly the notion of a flip graph. So you see here on the left side an edge flip. So an edge flip on a triangulation T, you get by looking at an edge, removing it, and then you get a quadrilateral. And if this is convex, then you add in the other diagonal. And that triangulation we denote by TE, if E is the edge which we flip. And of course, you can immediately undo this operation by flipping the new edge E bar again, and then you get back. So you can read this picture from left to right or right to left. Moreover, if you have a point of degree 3, an inner point of degree 3, I should say, then you can remove all the incident edges and skip this point, and then again you have a triangulation, because since if you have degree 3, you're generating a triangle. And again, you can read this operation from left to right and right to left, because if you have a point that has been skipped, then you can add this point in its triangle and connect this point to the 3 vertices of this triangle. So one of these two operations we call a point removal flip, left to right, or a point insertion flip right to left. And all these flips, which I have explained to you here, are called the Bistellar flips. So these operations, of course, are not arbitrary. I mean, if you look at the drawings up here, I mean, there are two ways to two interpretations of these drawings. So on the one hand, this drawing here, where I show the other edge as a dashed line, kind of suggests that this is a drawing of a tetrahedron. And actually, you have the same tetrahedron, and once you look at it from below and once you look at it from above. So this is the change you get here. Probably if you look above, you also have to do some reflection, and the same here. The other interpretation is, of course, just think about it. Suppose you look at this whole situation from below, and we are in this regular triangulation setting. Like we look at the lifting, and then we take the lower convex hull. Then in this picture here, there is a plane formed by these 3 points. You see my cursor here. I mean, Boris, do you see my cursor?
Yes, we see your cursor.
Yes. Okay, good. Thank you.
I can see the cursor too.
Good, thank you. So the plane formed by these 3 triangles has this point here above, if you have here the lower convex hull. And of course, if you start changing the 3rd coordinate of this point and you lower it, at some point, these 4 points become coplanar. And after that, you switch to this picture. So this is actually what you see here, and the same thing applies obviously on the right side. What you see here are the changes that happen if you look at the lifting and you change the y coordinates of the points. So these are the changes you observe while the height coordinates of the points change. So these are the flips. And let me just remind you that, of course, not every edge is flippable. So if the edge, after removal, sits in a non-convex quadrilateral, then we cannot flip it, and also we cannot flip any point which has degree larger than 3. All the skip points we can always flip, and of course the boundary edges and the extreme points, they are never flippable. So now we can define the bistellar flip graph. So the bistellar flip graph of B has its vertices. I mean, by now, I think it's clear to everybody what we are after. So it has its vertices, the set of all partial triangulations. And the edges are the pairs which differ by a bistellar flip. So all the edges, all the pairs that differ by this minimal operation. So this is the bistellar flip graph, and there is also the edge flip graph of all full triangulations. So if you just want to consider structure on the full triangulations where you cannot skip points, then of course you should not do any point removal flips. So you're just stuck with the edge flips. And so this is called the edge flip graph. And there is also the bistellar flip graph on the set of all regular triangulations. So if instead of looking at all partial triangulations, you just look at the regular triangulations. And what we are interested in is the vertex connectivity of these graphs. So how well connected are these graphs? And actually, I will later even give you a definition of what is the vertex connectivity of a graph. So I think now it's time to go through a few examples, and that will also allow me to provide some extra context. So here we have 6 points, so the vertices of a hexagon, and to the left you see all triangulations, all the 14 there are. And what you see down here is just a graph without the triangulations, and what you see here looks like the graph of a polyhedron, of a polytope, and that actually is always the case. So if you have convex position, Then the flip graph, which is, as we observed in this case, is the same as the edge flip graph or the bistellar flip graph or the bistellar flip graph of regular triangulations, because it's always the same in this case, is the graph of the so-called isocahedron, which is an n-3 dimensional polytope. So what you observe here for 6 points is true for any number of points in convex position. That's essential. So let's now go to the example which we have seen already. So here are 5 points with 1 point in the interior in this special setting here. And then the flip graph you get is the figure here. So you see on the outside here in the drawing, here are all the triangulations with the central point here skipped. That is what you see here inside is the edge flip graph, and the whole thing is the bistellar flip graph. And this is the graph you get. And as it so happens, this is again the graph of a polytope. So before everybody gets too excited about this, I should go to another example. So this is this one triangle in another, if you like. And this is the flip graph you get here. So you see here, for example, the triangulation which skips all inner points. And of course, you can add each of these inner points. You can add as a vertex of degree 3. So here you have the top inner point. Here you have the left inner point. Here you have the right inner point, and so on. And so the graph you can get here, in this case, you see here, and one can easily see this is not a planar graph. And if this were the graph of a polytope, it had to be a 3-dimensional polytope, because we have vertices of degree 3. And if it's not planar, we know that this is not the graph of a polytope. So the first examples we have seen were kind of special cases. In general, the flip graph is not a polytope. So let me go through another example. So here we look at 5 points. And if they are in convex position, then you get a pentagon. So this is the isocahedron of dimension 2. If you have 4 points in convex position and 1 point in the middle, then you also get a pentagon, nicely enough, which you see here. The full triangulations are up here, and here are the triangulations with skip points. And if you have a triangle with 2 points inside, again, you get a pentagon for the bistellar flip graph. So whenever you take 5 points, then the bistellar flip graph of this 5 points is a 5 cycle. And these 5 cycle therefore appear in every bistellar flip graph all over. So whenever you take 5 points and you look at the convex hull and you skip everything, every other point which is in this convex hull, and you take a triangulation of the outside of these 5 points, then in the inside you can start flipping in this 5 cycle. There are also 4 cycles. I mean, these you get quite easily. Suppose you have a pair of independent flips. So let me not formally define this, but imagine you have a big triangulation and you have a flippable element here, say an edge, and you have a flippable element point somewhere else far away from the first edge I gave you. Then you can flip the 2 independently, and that you can easily see gives you a 4 cycle. But there are no 3 cycles. So actually, if I go back here, then you see here, for example, you see these 5 cycles. And here you see a 4 cycle, and so on. So these 4 and 5 cycles are omnipresent in the bistellar flip graphs. and also in the edge flip graphs. So now we're getting closer to the result I'm trying to explain to you. So what is vertex connectivity? So for k, a natural number, a simple undirected graph is k vertex connected if it is connected, has at least k plus 1 vertices, and removing any set of at most k minus 1 vertices and their incident edges leaves the graph connected. So that's a very basic definition in graph theory. And here is a theorem in geometry which refers to this notion. And namely, it says that the graph of a d polytope, of a polytope of dimension d, is always d vertex connected. So for example, if you have a two-dimensional polytope, so which is just a polygon, then obviously this is two connected, because if I remove one vertex, I cannot get it disconnected. I have to remove two vertices. And for example, the cube is three connected. Whenever you remove two vertices, you will keep this graph connected. So now we know what connectivity is, so I can explain you towards the history towards the result. So Lawson in 72, he proved that the edge flip graph of full triangulations is connected. Actually, there's a nice story behind it. So he first had a paper 5 years earlier, which he then basically withdrew, and then he gave the full result. And he was really interested in this flip graph. I don't even know whether he called it a flip graph back then. But for practical purposes, because he wanted to compute good triangulations, and he had a heuristic that started with a triangulation and used flips to improve the triangulation. And that later also led to the Lawson algorithm for computing the Delaunay triangulation, for those who are familiar with this notion. So the Delaunay triangulation, by the way, is a very specific regular triangulation. And if you know the Lawson algorithm for computing the Delaunay triangulation, then of course this is also a proof that this graph of full triangulations is connected. It follows immediately that the bistellar flip graph is connected. That follows from the result above. I mean, just imagine you have two partial triangulations of a given point set. Well, if they're both full triangulations, then we can just use Lawson and connect them by a path. If not, you can take in either of the two triangulations, flip to a full triangulations by just 2-point insertion flips. Just take one skip point after the other and insert it as a vertex of degree 3. Then both of these triangulations have flipped to a full triangulations, and then you can connect the two full triangulations by a path according to Lawson. The bistellar flip graph of regular triangulations, so remember this is, you have the same flip operations, but you restrict yourself to regular triangulations. Well, this is connected by design. I mean, remember what I told you about what happens if you, one way of interpretation of the bistellar flips is that what happens if you change the height function of a point set. So if you have two height functions which give you two regular triangulations, you can just continuously move from one height function to the other and observe the lower convex hull, and the changes you're going to observe on the path are exactly the bistellar flips. I mean, you have to be careful to avoid degeneracy, but that's a minor issue. Okay, so the graphs, all the graphs you consider are connected. Now, by the things I have told you, the flip graph of endpoints in convex position, I told you this is a graph of an n-3 dimensional polytope. And by Balinsky theorem, which says that the graph of a D polytope is deconnected, it immediately follows that this graph is now n-3 connected. So this is for convex position. And then there is a celebrated theorem by Gelfand, Kapranov, and Selevinsky from the late 80s of the previous century, which says that actually this is a special case. The isosahedron is a special case of a more general theorem, namely that the bistellar flip graph of regular triangulations is the graph of an n-3 dimensional polytope, which is called the secondary polytope. And now in combination with Balinsky theorem, we know immediately that this graph is n-3 connected. And actually that what happened in example 2. So we had these 5 points with the point in the middle. And here you see the bistellar, the bistellar flip graph of partial triangulations. So this is actually, as it happened, this is the secondary polytope of this point set, because in this case, all the partial triangulations are regular. Actually, this is by a general principle. Not only if you have no interior point, all triangulations are regular. If you have only 1 or 2 interior points, then still all the triangulations are regular, all partial triangulations are regular, and therefore you get a polytope. So that's why in the non-example, where you don't get a polytope, I had to move to an example with 3 interior points. So now it naturally the question open, which was asked, for example, in the book by Jesus, Jörg, and Paco in 2010, is what about the bistellar flip graph of partial triangulations? How vertex connected is this graph? And that is the theorem we proved. So the bistellar flip graph of partial triangulations of any set of endpoints in general position in the plane is n-3 vertex connected. And this is tight. Actually, it's tight for every point set. We could actually go through the exercise and prove the tightness. I mean, just suppose you have n points. What we can easily prove is that there is always a triangulation which has only n-3 neighbors, which has degree n-3. And of course, if you have a vertex in a graph of degree n-3, you cannot be more than n-3 vertex connected, because if you have a lower degree, you just remove the neighbors of that vertex. So why is there a triangulation with n-3 neighbors? Well, just take the h extreme points, skip all the other n-h points, and look at the triangulation of these h extreme points with n-h points skipped. And clearly this is a partial triangulation in which you can flip all the h-3 inner edges of the triangulation. And there are another n-h flips, because each of the points skipped you can just add. So this is n-h plus h-3, so this is n-3. So these triangulations, as I described them now, which skip all the inner points, they have always degree n-3 in the flip graph. So let me say a few things about how we prove the theorem. So we start off with 2 little lemmas on connectivity. So even if you don't care about the results, I kind of like these lemmas. They are simple. Actually, I think if you ever happen to teach graph theory with vertex connectivity. I think these are good exercises to see whether the students understood what you did. So the first thing is what we call local Menger. And I guess some of you or many of you know Menger theorem. Menger theorem says that a graph is k connected if for any two vertices there are k vertex disjoint connecting paths. One usually says interior vertex disjoint connecting path because clearly the starting point and the ending point of this path are the same. So now this is almost like Menger, except that I have to start from a connected graph. So this is what I underlined here. But I have to look only at any pair of vertices at distance 2. So that's enough. So I don't have to look at all the pairs in order to get the graph k vertex connected. It's enough to look at any pair of vertices at distance 2. So Menger basically is if everything which is underlined here you remove, then you have Menger theorem, and local Menger is what we have here, which basically says that you can do this Menger condition, you can restrict in a more local way. There's another little lemma which turned out to capture exactly what we need. So as I said before, if the minimum degree of any vertex in your graph is delta, then you cannot be more than delta vertex connected. Because as I said, you can just remove the vertices of the neighbors of this vertex of minimum degree. Now the nice thing is if a graph has no four cycle in its complement, then you get the best possible connectivity. Then immediately you know that the graph is delta connected, the best you can possibly get. So this looks like a special condition here, and so it is, but it happens to be exactly what we need. And again, this is something you can give your students as an exercise to prove this little lemma. So the important thing is the graph has no four cycle in its complement. So I will not be able to give you the proof of the theorem I'm trying to present here. I'm presenting here, but what I want to do, I want to give you the spirit, and the spirit I give you by a little sidestep. I prove for you Balinsky theorem for d equals 3. So that's of course a very simple special case, but and so let's see. So what do we have to prove? So we are given a 3 polytope P, like the one you see here. We know that the graph is connected, and we want to show that it is reconnected. So by local Menger, it suffices to show that whenever you have 2 points U and W at distance 2, so like here, U and W, so they have distance 2, they have at least 3 vertex disjoint UV paths. So you find 3 paths from U to W, which are pairwise vertex disjoint. So of course, since they have distance 2, there is a vertex V, which has distance, which is adjacent both to U and W. And the way we find these 3 paths now is the following. We consider what is called the vertex figure of V. That is, we take a plane and we cut off the vertex V from the rest of a polytope with this plane. So you take a plane which has V on one side and all the other vertices of the polytope on the other side, among others, definitely U and W on the other side. So what you get by intersecting the polytope with this plane is a convex polygon. So you get a polytope of one dimension smaller. And of course, this is too connected, but the important thing is whenever you give me a path now on this cycle, you can map this path back to a path on the original polytope. So like if you go from here to here to here, that corresponds to a path you go from here to here to here to here. So that path now may be longer because like this edge here gets mapped to two edges, but you have this path, and it's also easy to see that if the path here are vertex or interior vertex disjoint, they're also interior vertex disjoint here. Now, since the cycle here, of course, is two connected, we know that we have here for this, from this vertex here, which corresponds to U, to this vertex here, which corresponds to W, we have two vertex disjoint paths, which we can map to path on the polytope. And that gives us two vertex disjoint paths. We need three. Well, it's easy. The third path is the path which goes from U to V to W. So this is the path here. Okay, so that proves Balinsky's theorem in dimension 3. I should say that on the one hand, this is not the way usually Balinsky is shown. There's a nice proof basically using linear programming or ideas from linear programming to do this. On the other hand, this proof here, which I explained to you in dimension 3, you can turn into an inductive proof for Balinsky in general, because what we basically said is we take the vertex figure of a vertex. We know that this is a polytope of one dimension smaller. There we know that it's d minus 1 connected by induction hypothesis. And so we find d minus 1 vertex disjoint path, and then you add the path u, v, w. Okay, good. But anyway, so this is kind of the basic idea. But you should not be confused here, because I told you actually that the Bistellar flip graph is not is not the graph of a polytope. So we have to be careful. This is just a piece of inspiration. So, but what we basically do is we mimic that the graph is a polytope. So remember, we have the local Menga, and we know that no 4-cycle in the complement gives min degree connected. So what we do is we look at our graph, the Bistellar flip graph, and we look at polytope features, let me call it this way, of this flip graph. So what do we have? We have vertices, we have edges, and we have two faces. Well, we don't have two faces naturally, but I define basically the 4 cycles and the 5 cycles, which I tried to emphasize when we went through the examples. So these I declare to be the two faces. So this is a definition in this context. And now we consider the link of a vertex in this graph. So let's see. So what did we need to define the graph of the vertex figure? So we have a vertex. So remember, this is in our case, in our graph, this is a triangulation. We needed the notion of an edge of adjacency, right? Okay, so that we have in our Bistellar flip graph. So we have vertices, we have edges. What we miss are two faces, because why did we connect this point here with this point here in the link of this vertex V? Well, because these two points, or rather the two edges from which they come from, they lie on the two face. And that's why we connected these two. The same here, these two lie on the two face, that's why they get connected. This edge here and this edge here, they do not lie on a common two face. So that's why this point and this point does not get connected, right? So we can at least define something like a vertex figure, and we call it here in this context a link of a vertex in this graph. And the nice thing is that everything which basically, which I explained to you for Balinsky, goes through now here in this setting. So we need again this operation that we can map a path in the link. Now we call it a link back to a path in the original graph, and we can do this in such a way that vertex disjoint path map to vertex disjoint path. Then we can show that this link here is n-4 connected, and that's where the second lemma steps in, because we can namely we can show that the link, as I defined it here, has no 4 circle in the complement. And then, of course, that's easy. We have to show that the minimum degree is n-4. Then we have this lemma. Then we have this is n-4 connected. Then we get n-4 path, which we can map back to path in the bistellar flip graph. And then we just add the path from this triangulation to this triangulation to this triangulation. So that's the proof we do, and I think it's in the end it turned out quite a natural proof, natural path which we could follow in this proof. Okay, I don't questions. I'm talking without interruptions. I'm getting close to the end. Boris, 45 minutes was how long I should talk, right?
I don't think I mentioned the specific duration. You certainly have 5 or 10 minutes more if you want to, or
yeah. Okay, so let's see. So what else can I say? As you see, I have another 8 groups of slides, but probably I don't want to go that far. So given the way I tried to sell to you the proof and the fact that there's this secondary polytope, I mean, the question is, how far away is the bistellar flip graph from a polytope? That depends on how you look at this. So one thing we can prove is that even though the bistellar flip graph of a point set, it is not necessarily the graph of a polytope, we can cover it by graphs of polytopes. So like, for example, this counter example we have seen. So this is not the graph of a polytope. We can write as the union, not the disjoint union, the union of this graph, which is obviously the graph of a polytope, and this graph here, which is obviously the graph of a polytope if you redraw it in the way I've shown it here, namely this is the graph of a cube. And so this holds in general. So you can always write your bistellar flip graph as the union in general, not just 2, but many more graphs of n-3 polytopes. So this is how far we, this is kind of one interpretation that this graph is actually close to graphs of polytopes. The building blocks you see here, these are products of secondary polytopes. So obviously an edge is a secondary polytope. So this cube, the cube here is a product of 3 edges, and then therefore it's a polytope. So here I can summarize the situation as we have it here. So we have full triangulations, which are a special case of partial triangulations, and there are regular triangulations, which are a special case of partial triangulations. Here we have the edge flip graph, the bistellar flip graph, and here also the bistellar flip graph of regular triangulations. By the secondary polytope, we know, and Balinsky, we know this is n-3 connected, so this was known. So we showed this graph here is also n-3 connected. I should emphasize that not only does this obviously not follow from the n-3 connectivity of the regular triangulations, but there's also no implication in the other direction. So if you think about it from the n-3 connectivity of the bistellar flip graph of partial triangulations, we don't get this for the regular triangulations. And this is always a polytope, an n-3 polytope, the secondary polytope. Here we can cover. And the similar thing holds for full triangulations, except that the n-3 now is n/2 minus 2 ceiling connected. And those people who thought a little bit about flip graphs know that this is the lower bound on the number of flippable edges in any triangulations, and therefore it's lower bound on the minimum degree in the flip graph. Clearly, here it's hard to generalize to higher dimensions, and I will say something briefly shortly. But here, the secondary polytope, of course, is not restricted to 2 dimensions. This holds in any dimension, and the n-3 gets to n-d minus 1. And of course, I would have to explain to you what a flip in higher dimensions is, but it follows the spirit of looking at the simplex from both sides. That's why it's called a bistellar flip graph, and take these operations as the building blocks of the flip graph. So what are open ends? So one is special position. So this is a non-trivial step, I have to say, to include degeneracies. I think it should work. So we are working on it, but it comes with all kinds of surprises. And some people have said, so why didn't you do it for special position right away? I mean, at least for me, I cannot speak for others. I would not have been able to get this or to get this result or even close to it if I went to special position right away. I mean, we can do now some manufacturing if it works to go to a special position. But some of the notions we needed that was just to go there directly is too much of a challenge. And I should also say that we do not claim the result for special position at this point. Higher dimensions. As I indicated, there is, of course, the notion of a flip graph in higher dimensions, and the book on triangulations I just mentioned works a great deal about higher dimensions, actually not so much about 2 dimensions. And interestingly, so starting dimension 5, the bistellar flip graph can be disconnected. And these were celebrated results by Paco Santos around the turn of the millennium. And I find it quite amazing that this question of the connectivity of the flip graph, so now we're talking just whether it's connected or not vertex connectivity. This is open in dimension 3 and 4. So even in dimension 3, we do not know whether the flip graph is connected. What we did here, I'm afraid, will not help in answering this question. Actually, and then that's probably an interesting thing to mention here. So in our proof of the n-3 connectivity, we were assuming the connectivity of the graph to begin with. We are not reproving Lawson's result. And the reason is because we use local Menger, and local Menger as a precondition has that the graph is connected. So if anything of what we are doing generalizes to higher dimensions, then what we could probably show is that, say, in dimension 3, every connected component of the flip graph is highly connected. But we cannot show, I don't think we can show something for the connectedness per se. And then there is a third question, and to some extent, this is also where we came from. Can we show expansion? I mean, there is one question behind all of this. And I'm not claiming that we contributed or made progress in that direction. But anyway, the question is, if you take a triangulation and we start you start flipping edges or points, if you like, randomly, so you keep performing random flips, then one can actually show that one eventually converges to a uniform random triangulation. The question is, how long is this going to take? Is this a rapidly mixing process? And this is known for 20 years now, roughly, if the points are in convex position. So if you have the triangulations of a convex polygon, then there is rapid mixing. I think the upper bound is something like an n to the 5th or n cubed. I don't remember. And there's a lower bound of n to the 3/2. But there is close to nothing known if you go away from convex position. And so that would be really nice. Okay, so I have some more material, but I think this is actually that's a perfect opportunity to stop here. Thank you very much.
Let's upload the best we know how to. For example, we could unmute. Questions, suggestions, comments?
Complaints?
I have a question, if I might. So it's Anna.
Yes. Hi, Anna.
Hi, Emo. I like the talk very much. One question is, what about a constrained triangulation? So the theory of Delaunay triangulations carries over to say if some edges are fixed, you're still connected.
Mm-hmm. I don't know.
Okay.
It's a natural question to ask, no question. But I don't know the answer.
And I have one other question, which is also perhaps, which is to do with mixing. The case of points in a regular grid is of interest to the physicists, but I don't think they're considering the bistellar flips.
Yes.
Do you know anything about that in your case?
I don't know anything about it, except that I was thinking about it. I mean, actually, with Jirka Matuszek many years ago, we were thinking about it. I have in my living room, I have a big artwork which shows a random triangulation of a 200 by 200 grid. It looks beautiful, I can tell you. So it's definitely a very nice problem, and just for this very special configuration of a grid, as you suggest. I mean, it would be nice to be able to say something about the mixing. Yeah, that's a very nice question.
You should have your background screen showing that.
Yeah.
Thank you.
Thank you.